Hello guys. So in this short video, I'm gonna once again review the topic of transformations of functions, and I'm gonna give you several examples, and hopefully you will get it completely this time. So let's begin. We have 6 slides to go through. 7 and 8 have nothing. So let's begin already. So the types of transformations that there are. You have three types basically. You have reflections, translations, and dilations. And the dilations are themselves classified in stretches and compressions, right? And we have the following. If f is any function whatsoever, the whole idea of transformations can be applicable to any function. It doesn't have to be specifically a quadratic function or a rational function or a reciprocal function. No, the idea of a transformation is completely universal. So let's see how this works. At the moment, I have seen that you manage quite well the reflections and the translations. So let's explain this very quickly once again, just in case. If you have a function f, then if you create another function g, and g is expressed as f of minus x, what that is, you multiply the input of f by minus, then what you're producing is a new function g, which is a reflection around the y-axis. And what does this mean? What does reflection around the y-axis mean? What it means is the following. If it happens that your function f looks like this, if this is f, the graph of the function f, let's suppose that, then the function g, if I'm gonna draw it, well, no, let's do it in the same axis, right? And if I'm talking about a reflection around the y-axis, what that means is that this is the axis of symmetry of the reflection, and any point in this graph, any point in this graph will be reflected about or around this axis, and so you're gonna have this, more or less. This point will be reflected into this one. This point will be reflected into this one. This point into this one, and so on. So you get the idea, right? This is what we know as a reflection around the y-axis, and this would be g. Okay. And on the other hand, when you have a function g expressed as minus the whole function f of x, the whole function. Okay, notice the place of the minus. When you multiply the whole function by minus, what you cause is a reflection around the x-axis. And what that is that this graph will be reflected around the x-axis, okay, and it's going to look like this, give or take. You see, this point gets reflected into this point into this point, and so on. So that's what reflections mean. Now, on the topic of the transformation of translations, we have two types: the vertical translations and the horizontal translations. Vertical translations is very simple. Basically, the function g is expressed as f of x plus a number k, and this number k can be either positive or negative, right? If k is positive, then we're talking about an upwards translation. And if k is negative, we're talking about a downwards translation, vertical translation. On the other hand, when g is expressed as f of k x plus k, and so you must notice that the k, the number k, the constant, is added to the input. You see, to the input we add x, or perhaps subtract x. And depending on whether we're talking about a plus or a minus, we will have different translations. For example, if k is positive, then the horizontal translation is leftwards, and if k is negative, then the horizontal translation is rightwards. Okay, and then these are the ones. Let me erase this for the moment. So these are the ones that cause trouble, in my opinion. The dilations, which can be either stretches or compressions. So first, let's assume that k is positive. I'm gonna I'm gonna make that assumption so that we don't get into too much trouble using absolute values and whatnot. So let's assume k is positive. If g, your transform function, is expressed as k times f of x, that is, you multiply the whole function by a constant k, then you have two cases. If k is greater than 1, if this number is greater than 1, then we're talking about a vertical stretch of factor k, right? We will explain what this means visually in a moment. And if, on the other hand, if k is between 0 and 1, what that means is k is a fraction, then we're talking about a vertical compression of factor 1 over k. Once again, we will talk about these two sentences in a moment. And when, on the other hand, when the constant k, it multiplies not the whole function, but just the input, as you can see here, the k is multiplying only the input, then we have as well two sentences of this type. If you notice, read this, you can pause the video and read this, and then next after that read this, and it's pretty much the same sentence except for this. You're changing vertical for horizontal, right? And you're changing stretch for compression. So when, in this case, when k is greater than 1, we're talking about a horizontal compression of factor k. And when k is a fraction between 0 and 1, then we're talking about a horizontal stretch of factor 1k. You see? So basically we are flipping, let me highlight this, we're flipping this for horizontal, and we're flipping stretch for compression. And the same in here, vertical, horizontal, compression, stretch. The remaining of the sentence is exactly the same, as you can see. Okay, now let's talk about these ideas, and let's see what they mean by means of examples. So let's jump right into the third slide. It says examples of unitary transformations. What am I writing this word? Why am I writing this unitary word? What I'm trying to signify with this word, guys, is that these are transformations that are just basically it's just one transformation, just one. Because as we have seen, and let me go ahead a little bit. For example, in this case, we can see that g is a transformation of this parent function, right? Take a look at this, take a look at that. So this is a transformation on the quadratic parent function, but it's not just one transformation, it's more than one, okay? So I'm calling this composition of functions because you're applying one function, one transformation after the other. And on this other case, I'm just applying one transformation. So that's why I'm calling them unitary transformations, okay? So for us, we can call them this way. So let's see what we have in here. We have the following. Given f of x equals x squared, and by the way, let me see if this is recording. Okay, it's fine. Given the parent function f of x equals x squared, which is the parent quadratic function, the simplest one, then draw the graphs of these 10 functions, okay? In each of these cases, g is a transformation, a unitary transformation on the parent function. So let's start very simply one by one. So what if g of x is equal to minus f of x? Okay, what that means is the following. That g of x is equal to minus x squared. And as we have seen in the previous slide, okay, what this means, when we multiply the whole function by minus, what that causes is a reflection around the x-axis, right? So we will have this. Since we know that the graph of this function looks like this, right? Then the graph of this function g is going to look like this. Sorry, like this. You see? So we're talking about a reflection around the x-axis. This is being reflected around the x-axis, and it's going to end up looking like this. So there you go. Period. Okay, next. What are we having here? We have g of x equals f of minus x. Now the minus is only being applied to the to the variable, right? Okay, so what are we having here? We have this g of x equals minus x squared. That would be the right substitution. Okay, and if you can notice right away, for the parabola, let me draw the parent function f. There you go. If you reflect this function around the y-axis, basically you're gonna end up with the same function, right? Because this branch will be reflected and it's gonna be looking like this, right? And this branch is gonna be reflected about the y-axis and it's gonna end up looking like this. So this is gonna be g. So it's very clear that in this case, for this particular function, given its characteristics, a reflection around the y-axis remains the same. Okay, and you can see it analytically from here. G of x equals minus x, all of this to the square, which is equal to x squared. You see, when you raise minus x to the square, you get this x squared. So you're gonna get g of x equals x squared, and what that tells you is that this function is the same as f. So there you go. There you go. So that was the first two. Now, well, let me erase this as well a little bit. Now let's talk about translations. These two are vertical translations, and these two are horizontal translations. Once again, I'd like you to open Desmos, right? And just graph, if we have this parent function, then write this this function g, which is f of x plus 2. We are adding 2 to the whole function, so it's going to be x squared plus 2. And what you will notice is that the function will go from here, which is the parent function. It's going to go 2 units up. We know this already, right? So this is done. And what this is going to do is it's going to bring the function, instead of upwards, downwards. So this is 2 units upwards, and this is 2 units downwards. Okay, I mean, this is 1 unit, 2 units, 1 unit, 2 units, right? So this is plus 2, this is minus 2. So this is this case, and this is this other case. Once again, from my experience with you, working with you guys these last weeks, I've seen that you manage these transformations quite well, as well as these two, right? What we're having here is horizontal translations in both of these cases, but just don't get confused, right? Most people would try to match the plus with the direction of rightwards and the minus with the direction of leftwards, but this is not what's happening here. When you have this type of translation, when you add 2 to the input, what you will cause is a horizontal translation of 2 units to the left. So it's going to be 1, 2, and therefore this parabola is going to end up looking like this. It's going to be moved 2 units to the left in this first case. And in this other second case, what you will have is this parabola being moved 2 units to the right. 1, 2, you're going to have this, more or less, right? So that's how it works. So once again, in my opinion, these first six transformations are quite understood by most of you at the moment. Okay, the ones that you have a little some trouble with are this type, right? This type of transformations. So let's analyze this first. We have g of x equals 2 times f of x. So it's going to be a constant times the whole function. And in this other case, it's going to be, once again, another constant times the whole function. What is the difference between this and this? In very broad words, well, the fact that this constant is greater than 1 and this constant is between 0 and 1. So it's a fraction of the unit, right? So let's see what happens. What is this in the first case? So let me write it in here. Well, let me use this space in here. G of x equals 2 times f of x. Let's make the substitution. G of x is going to look like this, 2x squared, because f of x is x squared, right? So this is going to be the function. And what this is causing, as we have seen in the previous slide, once again, this is going to apply a vertical stretch of factor 2. Now, what does that mean? What does that mean? This is what you have to understand deeply, guys. When I say the word, when I say the phrase, that this function g is nothing but a vertical stretch of factor 2. When I say all of this, what am I saying? What I'm saying is this. If you have your function, your original function, f of x equals x squared, looking like this, give or take, then the function g, I'm going to try to draw it. Well, let me redraw this a little better. There you go. And I'm going to only sketch the function g in the same Cartesian plane. So what's happening? If g is a vertical stretch of factor 2, what that means is the following. The function f, basically, the graph of the function f is nothing but a series of points, right? So point, 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 point. It's just a collection of many, many points. What's happening is this, guys. Something is happening to all of these points, in particular to their y coordinates. Okay, as you remember, every point has two coordinates, the x and the y coordinate. And when you're applying a vertical stretch of factor 2, what you're transforming is only the y coordinate of each of these points, all of these points. Okay, what you're doing is multiplying their y coordinate by 2. So for example, if the y coordinate of this point is, let's say, 1, okay, right here it's going to be 1, then this point is going to be transformed into this other point. Okay, the x will remain the same, the x coordinate, but the y coordinate will go to 2. You see? And the same for this point. Only the y coordinate of this point will be multiplied by 2. And what that means, or visually speaking, is that this point will be moved upwards. It's going to be transformed upwards in such a way such that the distance from the axis to this point, okay, now for the red is going to be twice that distance. You see, this distance from the red point to the x-axis is twice the distance from the blue point to the axis. And the same for every single one of these points. You see, the same for this one, right? The distance from here to here is going to be multiplied by 2, and it's going to be looking about here, give or take, and you're going to be having this type of transformation. You see? So this is going to be G, and the blue one is F. So that's what we mean by a vertical stretch of factor 2. And on the other hand, when we have something like this, let me erase this thing. When we multiply by also by a constant, but in this case a fraction, then we're going to have it this way. And what this is a vertical compression of factor 2. And what's happening is the opposite. Instead of multiplying by 2, what's happening to the original parent function, let me draw it once again. Let me do it better. Okay, there you go, more or less. Then what's happening is that to each of these points in this original graph, I am not going to multiply by 2 this time. If I'm talking about a compression of factor 2, I'm going to divide the y coordinates of each of these points, only the y coordinates, by 2. So that now this point will be transformed into this one, such that this distance is only half of this distance. And the same for each of these points. So if you took maybe a sample of points and did the same, right, you're gonna end up looking with something resembling this. So this is gonna be g, the transform function, and this will be the original function f. So that's what it means, guys. That's what vertical stretch of factor 2 means, and that's what a vertical compression of factor 2 means. That's what it means. And it's pretty much the same idea with, well, once again, let me erase this, with these two, with this and this. But now the only difference is that uh, when you multiply the input by a number greater than 1, okay, it's no longer going to be a stretch like in this case. It's going to be a compression of factor 2. And when the constant is a fraction between 0 and 1, this is going to be a stretch. And by the way, we're talking horizontal compression of factor 2, and this is going to be a horizontal stretch of factor 2. And it's the same idea, but now instead of applying the transformation on the y coordinates of these points, it's going to be on the x coordinates. So this point will be moved either in this direction in the case of a stretch, or this point is going to be moved in this direction in the case of a compression. But it's exactly the same idea. So if you don't understand this thing very well, I want you to make a pause in the video and try to play with the idea a little bit. Go to Desmos, graph this, this, and this, and try to relate what I just said to the functions. Try to really, really understand what's happening. Don't try to memorize, guys. It's a very, very bad idea. The best way to understand mathematics is by actually understanding the concepts, right? So there you go. Let's make this example now. What do we have here? We have the following. We have two functions in here, one blue, one red, and let's read. We have the red graph, this one, represents the graph of the function f of x equals x squared. So this is the parent function, the parent quadratic function, the red one. Don't lose sight of that. And the blue one, the blue graph, represents the graph of a function g. Write the equation of g as a transformation of f. So basically what I'm telling you is that the red function, once again, it's the parent function f, and the blue function, it's a function g, which is a transformation of the function f. And they're asking me to write the equation of the function g. So what's gonna g be? Is it gonna be a vertical stretch of f of what factor, or a vertical compression of f of what factor, or what's it gonna be? How can I find out? Okay, what you need to do is this, guys. First of all, I mean, you realize right away that g is not a reflection, right, of f, because I think, I mean, that's quite evident, and it's not a translation, right? So this is kind of like a vertical stretch or vertical compression, or horizontal stretch or horizontal compression. So let's see. What you need to do is this, guys. Try to locate some points on G, for example, some points that are easily, I guess, spottable. I don't know if this is the word. Like you can find quite easy. For example, this point right here. Look at this point. Okay, this point is 1,2. And then what you should notice is this, that this point could correspond to this one in the original function. You see? There is kind of like this correspondence. And basically, you could understand right away that G is a vertical stretch of factor 2. It could be this. Let's see if that's true. Why do I say this? Because if you take the function f and you take this point in particular, which is 1,1, you can see that if you multiply the y coordinate of this point, the y coordinate by 2, it ends up in here. So you see, so this point is going to be transformed into this point. And what that is a vertical stretch of factor 2 on this point. You see, we're vertically stretching this point by a factor of 2, and it finishes at this point. And the same has to happen to all of the points of f. Let's see if we can find another example of this. Look at this point. This point is quite noticeable. You see, it's the point 2 comma 4. And let's see if the y-coordinate of this point is being multiplied by 2. So what is the y-coordinate? Is 4. So is this 4 being multiplied by 2 and arriving at 8? Let's see. There you go. It's this point. You see? So 2 comma 4 is being transformed into 2 comma 8. So in fact, the y-coordinate of this point, which was 4, is being transformed into 8, which is twice this number. You see? So yes, it's a vertical stretch factor 2. That's enough. Maybe just a couple of points, making sure that they, let's say, satisfy your hypothesis. This was my hypothesis, right? And yeah, that's it, right? So it's that simple. So now that I know that G is a vertical stretch factor 2, and now that I know how to write analytically a vertical stretch factor 2, all I do is this. I just write this, and therefore g of x equals 2x squared. You see? So it's just a matter of practice, guys. It's just a matter of practice. Solve as many examples as you can from the book. Let's see one more of this. So same exercise. The red one is the original function f, and the blue one is the transformed function g. So my suggestion is make a pause on the video and try to write the equation of g, which is the transformation of the function f. Make a pause, take some minutes, and then come back. Okay, so what I can notice here is this, guys. For example, I can notice that, this point here gets translated into this one, but this is not noticeable. Like, I really don't know what value this is, so let me try to look for something else. Maybe, okay, look at this one, 3,9. Okay, so I think this is a good point to analyze. This point, which is apparently being transformed into this one right here. Okay, so what are the coordinates of this point? The coordinates are 3,9. And what is happening? What I observe is that the y-coordinate, which is 9, is being transformed into 3. You see? 3,9, 3,3. So what's happening? Apparently, the y-coordinate is being divided by 3. So let me put a hypothesis. We're talking about a vertical compression of factor 3. Let's see if another point helps me confirm the hypothesis. So if that's what's happening, then this point, guys, which has a coordinate of 6 in the y-axis, right? Like a y-coordinate of 6. I don't know what the x is, but this one is 6. The y-coordinate is 6. So this point, if I continue vertically, should end up in the third of this, which is 2, right? So let's see. Let's go down. It's right in here. So no, it doesn't seem like that's what's happening, right? 2 comma, if I go completely downwards, it's almost the case, right? But it doesn't, it's not quite there. So once again, since I can't remember what was this example, I'm sorry. Let me make a pause, and because I don't want you to lose time here looking at me trying to find the answer for this one. Let me make a pause and then solve it, and then I'll be back with you. As a matter of fact, it is, guys. I'm just getting confused with the drawing. It's quite tiny. But this point right here, which is at 6, if I go completely downwards, yeah, it goes to 2. Yeah, it's right. So this is a vertical compression of factor 3. Okay, and look at the number 3. This point right here, which has a coordinate of 3 in the y-axis. The y-coordinate is 3. If you go completely downwards vertically, it goes to 1. So yeah, the hypothesis was correct. G is nothing but a vertical compression of factor 3 of the function f. So how do I write that? I write it this way. 1/3 times f of x. What I'm saying is that g is a vertical compression of factor 3 of f of x. And so this is the equation. There you go. Okay, let me make a small pause and I'll be back with you. Okay guys, so now for the final part of this video, let's talk about composition of, well, not functions. I made a mistake in here. What I was trying to say is composition of transformations. There you go. So let's do this exercise. It says in the next 3 examples, G is obtained by applying more than one transformation on the function f of x equals x squared. And I need to do these 2 things. A, I need to arrive from f, arrive at G by a succession of unitary transformations. So what I mean is this. Well, and B, sketch the graph of G. So what I mean is this, guys. Let's look at this example. As we can see, G is a transformation. It's a transformation of the parent function f, but it's not just one transformation, right? It's not just a single transformation. It's 2 of them. By now, you have enough experience to identify this simple case, right? Which is what this plus 1 means is a horizontal translation of -1 on the parent function. And what this -3 means is apparently a vertical translation of -3 units, or vertical translation of 3 units downwards. So that's what it seems to be, right? But how can I be convinced of this, of my hypothesis? Okay, what I do is this. I'm gonna, from F, arrive at G by such succession of unitary transformations. Okay, so let me write f. I need to put f like so, and then I'm gonna successively, by unitary transformations, by the application of unitary transformations, get to G. Okay, so first, let's do the first one. Let's apply a horizontal translation of 1 unit to the left, which is supposed to be this, right? So let me call this function, let me call it now let me, well, f2, f2x. I'm going to call this f1, okay? The parent function, that's f1, and this of index 2 means the first transformation. So let's see, I'm going to apply a horizontal translation of 1 unit to the left. What that means is this, right? What I'm saying is that f2, now you know what, I think the subindexes is gonna get you a little confused, so let me use other letters. Let me use h. So h is gonna be this, and what is this? It's a horizontal translation of 1 unit to the left on the parent function. So let's apply it. So f of x plus 1 is gonna be x plus 1 to the square. So there we go. We are at this point so far. Now I take this current function and I'm gonna make a transformation on this once again. And let me use the same type of arrow, this one. So from here, I'm gonna jump here. And let me call it S. Okay, so now X, what it's gonna be is gonna be a vertical translation of 3 units downwards on H. So it's gonna be H of X minus 3. So as we can see, S is a vertical translation of 3 units downwards of h. And let me execute it now. So s of x equals h of x, which is all of this. And then the minus 3, I just write it down. So look at this. This is my final function after these two unitary, this one and this one, right? This is the first transformation. This is the second transformation. And I arrive at this. This is my final result. Okay? And as we can see, the result is actually G, as you can see. So what is the conclusion? The conclusion is that G is, in fact, the application of these two transformations in this order. Now, in some cases, guys, the order doesn't matter. For example, if you try to do the same exercise by first applying the vertical translation downwards and then the horizontal translation to the left, you're gonna get the same. So in some cases, it's completely irrelevant, but in the general case, it may be different. So there you go. So that's what G is, and this fulfills the first letter. And then B, sketch the graph of G. Once I know what this represents with respect to F, let me erase the whole thing. I already know what it means. So what does it mean? It means a horizontal translation to the left and then a vertical translation downwards. So what's going to happen is the following is going to happen. This is my original function, and then I translate it to the left 1 unit. So 1, 2, and it's going to be like this. Okay. And finally, I'm gonna pick this and I'm gonna move it 3 units downwards. So it's gonna be 1, 2, and then 1, 2, 3, and this vertex that is right at this point is gonna be located now here, and this is what you will have. So this ends up looking like this. This is this. Okay, there you go. Now what about the next? Let's see. Number 2, g of x equals 2 times x minus 2 squared plus 1. So it's pretty much the same as this. What we can see is that there is something being, in this case, subtracted to the input. And then we see another constant in here remaining. And then as an addition, we have a 2 multiplying this part of the function. So let me make a hypothesis. My hypothesis is that first, a subtraction of first a horizontal translation of 2 units leftwards. That's what's happening. And second, a vertical translation of 2 units upwards. And third, what would this be? This would be a vertical stretch of factor 2. So I can put this hypothesis. Now I'm being wrong, guys. This is not correct. But let's just for fun, let's practice with this. Let's assume that this is my hypothesis, and let me try if this is in fact what's happening, right? So what would I do? I take my function f, so f of x equals x squared, and I execute each of these transformations, 1, 2, and 3, in this order. So first, I'm going to apply a horizontal translation of 2 units leftwards. What am I going to have? I'm going to have this function h of x, which is going to look like this. X minus 2 squared. There you go. I have already executed this one. There you go. And then I am currently here. And then I'm going to transform this function and create a new function s, which is going to be a vertical translation of 2 units upwards of my current function, which is going to be this whole thing plus 2. There you go. No, 1. Plus 1, sorry. Plus 1. This is a number 1. Okay, so I have already executed this one as well. And finally, a vertical stretch of factor 2. So let me create once again another function. Let me call it r of x is going to be a vertical stretch of factor 2 applied on what function? on my current function, which is this one. And with a vertical stretch of factor 2, I need to multiply the whole function, all of this, all of it, by 2. So it's going to be 2 times s of x. And if I execute, I'm going to have r of x equals 2 times all of this. It's going to be like this. Okay, and as you can see, if I multiply the 2 by the whole parenthesis, I'm going to get 2 x minus 2 squared plus 2. So this is going to be my end result. 2 times this binomial to the square plus 2, which is not the same as g. So what is my conclusion? My conclusion is that g is a transform function on the parent function f, but not in this order, or it's not this particular series or succession of transformations. You see? So this was a wrong hypothesis, and that's how you can prove your hypothesis, or that's how you can confirm them or reject them. So what's the good one? With enough practice, you learn how to go from the parent function to whatever thing you have, even in your mind. So what you're doing basically is this, guys. You're first doing this, the multiplication by 2, right? Like, take a look at this. F of x equals x squared. Let's apply a multiplication by 2 of the function. So you're going to have this 2x squared. And at this moment, what I have executed is a vertical stretch of factor 2. That's the first thing I'm doing. And then I'm currently here. And then I'm going to create a function s, which is a horizontal translation of 2 units rightwards. So it's going to look like this. Okay, so this is horizontal translation of 2 units leftwards, to the left. No, sorry. I'm sorry. This was supposed to be a minus. And if it's minus, it's to the right. To the right. And finally, I'm currently here, and let's create a new function r, which is a transformation of this function. What type of transformation? A vertical translation upwards of 1 unit. So I take all of these and I just add 1. There you go. There you go. So this is a vertical translation of 1 unit upward. Okay, that's it. So this is the correct order. First, in order to go from here to here, which is all of this, as we can see, this and these are the same. In order to go from here to here, guys, or to here from here, which is the same, what I need to do is first a vertical stretch of factor 2, then a horizontal translation of 2 to the right, and then a vertical translation of 1 to the left, to the right. You see? So that's how it works, guys. That's how it works. Now, just as an exercise, I leave you this one. Let me give you the answer for this one. I'm not gonna do the whole thing. I want you to do it, and just let me tell you the answer. What's happening in here? In order to go from f, in order to go from this function f to this function g, what are you supposed to do? 4 transformations are taking place. 4 transformations. First, it's a reflection around the y-axis. That's what's happening. A reflection around the y-axis. Next, a vertical stretch of factor 2. Then a horizontal translation of 1 unit to the left. And finally, a vertical translation of 3 units downwards. Okay, all of these are taking place. Now, there can be slight differences. For example, this is a correct order, or if you change, for example, if you change these two, that's going to be also correct. Okay, so you see, there can be some slight variations all of which are correct. But this is correct. At least this is correct. And I want you to invent a type of transformation which is not in the correct order. Okay? So there you go, guys. I think this is enough. I hope you have understood as much as possible of this topic. And see you later.